Okay, this one we'll do problem 726. So this one's pretty straightforward. It gives you the properties and it wants you to find the maximum transverse shear. All right? So, you know, again, what we'll find with a lot of these things is we need to find where V is maximal, you know? Which point along the beam is V maximal? Once we know that, computing Q and I we'll get from here, right? This will allow us to compute Q and also I, and obviously T, right? T is 1/2 of an inch. Then you just plug it into the shear formula, and that gives you the maximum shear, all right? So this is pretty rote, right? Just computing the geometric properties. We've done that countless times. But I guess the only real wrinkle in this problem is actually having to get the shear diagram and then figure out where the max shear occurs. All right, let's start off. Let's do the simple part. Let's get Q and I. All right, zoomed out a little bit too much, or zoomed in a little too much, I should say. I'm losing some of my page. All right, so let's get the geometric properties, Q and I. So if we look at this cross section, we'll call this, I should say this, I've done I-beam so many times I should just have the equations closed form. So the web, we'll call that section 1, and we'll call this section 2. So the area, well actually on that one I don't need the area because it's around the neutral axis. So the I is going to equal the I of section 1 plus 2 times the I of the flange, because there's 2 flanges. This one we'll have to shift using parallel axis, right? Okay, so the I gives me I for section 1. It's 1/12 base times height. The base is 1/2 of an inch. The height is 6 inches. It's nice it gave me that way so I don't have to really do any subtractions. So that's cubed. Okay? And then 2 times the I for section, the flange. The flange, its I around its own neutral axis or its own centroidal is 1/12 base times height cubed. In this case, the base is 4. The height is 0.75 cubed over 12. But then we have to shift it by parallel axis. So the area is going to be the base times the height, which is 4 times 0.75 or 3/4 of that, right? So that's really 3. And then times the distance from the neutral axis to its centroid. So this distance here, which is going to be the 3 inches plus 3/8 or 1/2 of 0.75. That's 0.375, right? So that distance is going to be 3.375, and that gets squared because it's parallel axis, right? Area times that arm squared. All right, so let's get the numbers on that. This is all inches, right? We're all in inches on this one. But be careful, we got feet up here. So 6 enter 3 is 216.5 times 12. So this gives me 9 inches cubed. I'm sorry, inches to the 4th plus 2 times this is 0.141, that's inches to the 4th, plus this term here gives me 4 enter 0.75 times, that's 3.375 enter, square that times. This is of course the big one. Really the effect is by shifting it through parallel axis, right? That's what really gives you the dramatic effect. Then we add those all together. Again, you can see actually the eye of the flanges is 68 as compared to the eye of the web is 9 inches to the fourth, right? So the web has very little effect in comparison to the flanges, but the area of the flanges really isn't all that much anyway, right? Okay, that's the eye. All right, we also need to get the Q at the cross section, so let's do that in here. A little space in here. Q for the cross section, so that one. All right, we just have to consider from the neutral axis up. That's the neutral axis. So again, we'll call this shape 1, and that we'll call shape 2. We only have one flange in this case, so the Q is for 1 is going to be its area, which is the base, 0.5, times the height, which is just half of that. That's 3 inches, okay, times the distance from the neutral axis to its centroid. That's half of this height, which is 1.5 inches, all right? That's the that's the Q for section 1. And then if we do the Q for section 2, its area is going to be 4 inches times 0.75. That's the area. And its distance from its centroid is the 3.375 that I had computed before, right? That's the Q for section 2. We'll add those together, and that gives me a total Q of this is 2.26, or sorry, 2.25. This is 10.125. And so the total is 12.38. Well, actually, I'm doing 3 centimeters, so I should do 12.4. That's inches cubed. All right. So now we've got the I and the Q for those sections. All right. The T is obviously going to be the thickness at that midpoint. That's the 1/2. So we just need to compute V. So let's do the shear diagram. All right. I'm going to have to get the reaction forces, so we got to do a little work to get some of these reaction forces. All right, let's okay, so we've got a force at A and a force at D. Those are the reaction forces that we're going to solve for. So we do sum of forces in the Y. Force at A plus the force at D has to equal the net downward force. So this netward downward force here, I'm going to draw the effective force, so I probably won't need those again. No, actually I really won't. That'll help me. This one has a net down force of 150 over 6 feet, right? So that's 6 times 150. That's 900 pounds. And it's going to act at this distance here of 3 feet, okay? This one is going to have an effective force that acts at 1/3 this distance, so 1/3 from here. So this is actually going to be 2 feet, and then it's 4 feet from here, right? Because it's a triangle, so it's effective when it acts through the center. And then its net force is the area under the curve, so that's 1/2 the base, which is 6 feet, times the height, which is going to be 200 over the 6 feet. So it's 6 times 200. So that gives me 3,600 pounds acting at that point. Okay? All right. So that means that these two forces are going to sum up. Those add together. They have to equal the 900 plus the 3,600, which is going to be 4,500 pounds. Okay? Now let's do sum of moments. Let's do sum of moments around point D. Let's do sum of moments. This is about the z-axis, about point D. That's obviously going to equal 0. So we have the FA, all right? And that's a positive moment. So FA exerts a negative moment, so we have a minus FA. Its moment arm is 12, it's 14 feet. This 900 pounds force is a positive moment. Okay? And it acts on its moment arm, which is the 14 minus 3, which is 11 feet. This effective force here is also going to induce a positive moment. So it's the 3,600 pounds, and its moment arm is 4 feet. And that all has to go to 0. So that's going to give me FA is equal to all this stuff. 900 times 11 plus 4 times 3,600 divided by 14. Okay? And that's equal to that gives me 1,736 pounds. And then, of course, I can subtract that from this, and that'll give me the force at D. So that'll give me the force at D is 2,764 pounds. All right, so now we have the two reaction forces, right? This one here is 2,764 pounds, and this one here is 1,736 pounds. All right. Now we can compute the shear diagram, okay? So let's get another piece of paper. It's getting a little crowded here. So let's start from the left side of the beam, all right? So the first section we'll take actually will be through here. All right, now on these ones, you know, you can't really use the effective point force. You actually have to deal with the distribution loads, right? So this distance here is going to be x. That's positive phase, so this is the positive moment. Actually, I really don't care about the moments. The only thing I care about are the shear. So the shear, the positive shear is actually downward, okay? Because we're just doing shear diagram. And this is going up of 1,736 pounds. And then we have acting downward this uniform force of 150 pounds per foot. All right, so if x is in feet, now this gives me the fact that V is equal to the 1,736 minus 150, I should put pounds here, pounds per foot, times x. All right? That's for x between 0 and 6 feet, just up to that point. Okay? Once we get past that, now we do it from 6 feet to 8 feet, right? We'll see this coming up. Actually, now since we're doing the shear diagram, again, here's V. We'll have this downward force distributed. Here we'll see the whole length of it, so we know that this has the net 900 pounds down. So actually at this point, the V is going to equal 1736 minus the 900. So that's 836 pounds. So it's going to be uniformed on that section, all right? I can actually draw that. I should probably start sketching the diagram over here, right? So here's V. Here's 6 feet. There's another 2 feet, and then here's the final 6 feet. Okay, so from here to here, this is what we get. We start off at x equals 0 at 1736 pounds, okay? And then it has a slope that drops down with minus 150, so that actually at this point at 6 feet, we're going to come down to the total of 836. So that's about a half, that's about here, right? This is about 836 pounds. That's where we'll go to here. So this comes down like this. Okay. I know it's going to be 836 because this is actually right at x equal to 6. You get the 900 here, so this is actually what you get. Put in 6 here, you'll see you get 900. So it goes down to 836. Now that's going to stay constant along this whole stretch here, okay? And then finally, we have to consider this segment here. It's going to have, well, I'll even take a little shortcut. I know right at the end, the shear, if you look at this sort of the right half end, the very end of the beam, right? Let's look just at the very end of the beam. Right at x equal to L, so right where this distributed load has no effect. The only thing we see here is the 2764 acting up. This is a negative phase, so the positive sense of V is up. So right at the end where this has the downward force here is basically 0 because this, we're going to take the limit as this goes to 0. This is going to be just equal to the negative of this. So this is equal to minus 2764. So right at the end, I know you have to go down to minus 2764. So that's like down here, right? Minus 2764. So somehow we have to get down here. So it's going to have this sort of, since here's the bigger part of it, we're going to have this a quadratic effect, and it's going to kind of come down like this. So this won't be a straight line. This will be like a quadratic. Then the inflection will be positive. Okay, so the curvature will be increasing, right? So it'll actually look something like this. All right, we can get the shear actually at the right end. Let's actually analytically get this equation just to make life go a little better, right? So if we do that, let's pick a section that's a finite distance away from the end. Here we have the 2764. Again, the positive shear is acting upwards, and I have now this distributed load. This distance here is going to be the total length which is 14 feet minus x. All right? Now, if this is 14 feet minus x, I can get the effective force of this. This triangle, we can approximate with a point force, whose distance here, well, actually, the distance doesn't really matter because I'm going to give you some moments, but if you wanted to get them, this distance here is going to be 14 feet minus x over 3, right? And the total value here is going to be 1/2 the base, which is 14 feet minus x, times the height. And the height of this is going to be the slope, 200 pounds per foot, but that evolves over this distance. So that evolves over the 14 feet minus x. So this force here actually will have a value of 100 times 14 minus x. This is feet squared. Okay? So that's that quadratic. All right? That's the quadratic. Okay? So the net shear, I'm sorry, now I can do some forces in the y. I get Vx equals to 100, 14 feet minus x, quantity squared, minus 2764. That's the curve that's shown there. Okay? All right. So where's the maximum shear occur? Well, as is usually the case with these sort of beams, you usually get the max shear at the ends, unless there's, some sort of other way of offlet, unless it's free end. But usually the fixed ends, where it's pinned, you get the max shear. So this is the V, actually. This is where Vmax is, right? That's the one where we want to do VQ on IT. And that's going to equal to minus 2764, right? All right, so let's do that. Now we can get that the tau is VQ on IT. The V is 2764 pounds. The Q we got before is 12.4. That's inches cubed. The I is 77.6 inches to the fourth. Remember, this is where the max is. That's right at the neutral axis. So that's the Q from the neutral axis to the upper fiber. And then the thickness of the web at that point is 1/2 inches. And so when I do all this, I'm going to get PSI, and this gives me minus 883 PSI. That's the shear stress, okay? It occurs right at the end, at the neutral axis. Okay?